continual learning is a specific, let's say, an area of machine learning, I would say. And so this picture that you see over here, this by this green block, I mean a learner. A learner is any machine learning model per se, and this is a task that is given to the learner to learn. So this can be this is not anything continual. This is a standard machine learning setting where you are supposed to learn a model for solving a specific task. And so I mean, some things to note over here is like you'll be given a lot of data points for each of the tasks, and all these data points will be used by the learner with a specific learning algorithm inside it to kind of like learn the task, right? So give a concrete example, it can be, let's say, learning a set of classes for a classifier. Let's say we have CIFAR 10 dataset with us, and then we are supposed to learn all the classes in CIFAR 10. So it's a standard learning setting that we have. Now, in a continual learning setting, the same model. So over here, there was a learner, and now it got flipped over to a continual learner. A continual learner will be tasked to solve different tasks at different point of time. So the x-axis over here would be time. You can take it as time. So at time t1, you'll be tasked to learn. I mean, like you'll be basically tasked to learn task 1. And then again, the same model will be kind of introduced to a second task. Now, so this might ring you some bells where, like, this is something like a fine tuning, right? So what's a big point? Like anyway, you do have the task 2 data points, and then you fine tune the model on task, task 2. So what's the big deal? Now over there in fine tuning, we are not bothered about how good the model would be performing on the previous task 1. So in a continual learner, you are supposed to learn all the tasks that are seen till then and be performant in all the tasks that are seen till then while you're learning something new. And this can go on and on till, let's say, infinity, where incrementally you'll be learning different tasks. The task is a very vague name, I would say. And it can be different things. For example, so a task can be a set of classes to be incrementally learned. For example, we learn cows, dogs, and cats in the first task, and then in task 2, we're introducing the model to some other kind of task some other kind of classes. For example, let's say cars and motorbikes and trucks and so on and so forth. And the third task can be, like learning some other household items, or rather like some electronic stuff, like a laptop or a mobile phone. Now here, then the final model that we end up with should be performant on all the tasks. It should be able to classify the electronic gadgets that we have made the model learn at last task. At the same time, all the cats and dogs and the trucks and the other vehicles that we have learned as part of task 2. At the same time, task can be something completely different, as task 1 can be learning, let's say, segmentation for a specific data set, and probably task 2 can be, can you extend the segmentation model to do detection, or the other way around. You have a detection model and you're trying to extend the model to to perform something like like a classification, or rather segmentation, or so on and so forth. So or else it can be something like there can be domain shifts. For example, you try to learn a model on, let's say, MNIST, and then next you are supposed to learn a model on CIFAR 10, or rather, like, let's say, on SVHN. So the domain, so the number of the classes are same. Everything is just numerals from 0 to 9, but at the same time, the domain changes from MNIST to let's say to SVHN. So over there, the important part is, after learning SVHN as part of task 2, you are supposed to be competent on trying to classify digits on MNIST also. The important thing to note over here is machine learning models, or rather not machine learning models, I would say deep learning models actually fail in this specific setting. For example, if you are kind of fine tuning for a new task, the machine learning model, or the deep learning model that you're actually training, completely breaks down. Sorry. Yeah, completely breaks down when you try to learn something new. So I think this can be a simple, quick exercise that you can probably do and confirm yourself that this is actually the case. take a model, fine tune it on a new data set, and see how it's actually performing on the previous data set per se. And this is a quick example that you can just try out and see how difficult this kind of continual learning problem is as such. At the same time, it's worth noting that, it's something, um, it's worth solving too, because fundamentally we just cannot have all your data points with us at any point. For example, there can be privacy concerns, there can be storage concerns, there can be computational bottlenecks that we have. So one of, like the most naive way to solve continual learning would be, after you are learning task 3, keep all your data points of task 1, task 2, task 3, and then train a model again from scratch. Yeah, with all the data points. Now, this is not feasible. So we rule out such, like simple uh, simple ways of addressing continual learning by, like imposing some constraints. For example, we are not supposed to store all the data points of all the previous tasks when you're trying to solve something new. So this is continual learning. So I believe this is clear, and just as I told, initially, like whenever you have some questions, please speak up. Okay, so in this specific work, we trying to address this problem of continual learning uh, using a specific approach. Now, so whenever I try to kind of like formulate something that would be worth investigating, it should actually, like feel very close to my heart, or else I will not spend much time on that. So that's my nature. So and always I would prefer to have some correlations between systems that actually do these things very well. And one system that does continually learn, and the best way would be all of us, the human beings and the human brain. So there are studies in medical literature that actually says, you have this hippocampus and the neocortex inside the brain, right? So this hippocampus is an area of your brain where, there are a lot of things that are coming in. And so it's a short-term kind of a memory, where you'll be learning a lot of stuff over there, and a lot of things will be happening there. So it's actually a short term, and then what happens while you sleep is, like in the slow wave cycle of sleep. These concepts that are in the hippocampus gets consolidated into your neocortex. So this is biological evidence to kind of prove whatever I've just told right now. And this to me is really startling, that there's this two set of, memories, I would call them, or rather storage mechanisms or learning mechanisms, which has differential way of learning. One is pretty quick. At the same time, the other bit is a bit slow. At the same time, but there's one stark difference that is there in how we actually process. We don't store data points. We don't act in the space of data points, I would say. But then we always store concepts. So there is this the piece where you kind of go from the data space to this concept space, I would call them. So and the consolidation as such actually happens inside this concept space. So these are, like a few pointers from which keeps me going, or rather, these are very, very interesting concepts where, if we are able to do anything one-on-one with whatever we have over here in a deep learning setting, that would be great. But then we don't know how to do that. Yeah. But given such a motivation, I was kind of curious in drawing two things, to be specific. One thing is, let's not work in the data space, but then, like, let's do things in the concept space. Now, what's a concept space and consider? In a deep learning network. Okay, that's something that I need to kind of address to have that. And the second thing is, like, and this consolidation as such happens in this concept space and not in the actual data space. So I was trying to kind of like, link this together with, our machine learning setting, or a deep learning setting, and MERLIN is exactly something that actually does that. So it says, the MERLIN actually starts, it's just a short acronym for Meta-Consolidation for Continual Learning. Now, consolidation, I took that word directly from our brain literature. So we need to consolidate. and then it's doing a meta consolidation. So we are consolidating not the data points but the models, and this is good for continual learning. So that is MERLIN. So to be concrete, I assume that the weights of a neural network for solving tasks to be p in a psi given t. And then continually learning in this parameter meta space is actually really helpful. So this is the thesis that with which I start off. I mean that there is a meta space, and just trying to correlate between whatever I said and like whatever I'm doing. And then I do have this, continually learning in this meta space, or I would call that concept space. And I believe that would be helpful. And in advantages. So we actually work in something known as an online continual learning setting. So an online continual learning setting is a setting where like get to see a data point only once. Once you see a data point once, you cannot kind of that's this natural setting that we all of us kind of operate on. So that's and our method actually works in that space. And we are task aware and task agnostic. So I mean to simplify what exactly it is, going back to task 2 and task 3. So there is one league of continual learning methods which actually say at inference, where you're trying to infer something over here, you have the task label information. For example, you're saying, I need to solve, let's say, task 1, and then let the model a very restrictive way of continual, I would say. So our model that actually works in the task agnostic setting, as well as like if we have task information, we can definitely go ahead and use that too. So that is where our method actually works in continual learning. And I think I did allude what these things are, in the right beginning. And then we are able to do kind of ensembling of models. So all of us know that like ensembles are kind of like very powerful, very successful, because the way they need to be integrated into the learning, it was not very natural to kind of have that. But our model, like very naturally kind of have that extra push in it, where you can like, as we are learning the distribution over the weights, we can sample our weights from this distribution and ensemble them and go ahead. So yeah, that being said, so that is what MERLIN is, and like what all are the kind of features of MERLIN. So I'll briefly introduce the overall methodology of MERLIN, and I'll probably spend some time explaining each of the individual pieces that you see over here. But initially, let me give you an overview. So concretely, we are trying to solve a classification task over here, and each task contain a few set of classes that we want to learn incrementally. So in the first set, the first step that we kind of do is like we train a set of models on. So these are deep learning models. This can either be MLPs or this can be coordinates. So these are just coordinates which are kind of trained on a specific task T. Let's say the T1. We are trying to learn the first task. We have some data points for the first task. We train the model. We train a deep learning model on one set of data points that are sampled from the data points that I have. So this is just because I'm actually subsampling a few data points from all the data of all the data set of all the data for the specific task, training a model, storing it as like the Psi1, and then again resampling another set of data points, and then like training the model again. And like that would be my second like the Psi2 that you have over there, and then this is repeated for b times. So I do have B-based models, and each of the B-based models are actually learned from a same static initialization. So all these B models can solve the specific task one to be exact, very well. So that is the first step in our methodology. The second step would be to learn a parameter distribution. So what we have over here is like we have a set of parameters, right? I mean, like all the size are parameters. Now each psi is actually, I mean, like picked up, and we're trying to learn a parameter distribution, or rather that this p, the I mean, p theta psi that you just saw in the first slide. So this is quite similar to a variational autoencoding kind of a thing, area from which we can kind of like sample the data points as we need. So, but this is very different from a standard VA in one specific setting where, like it's the prior. So I'll get to this.
Excuse me, Joseph. Yeah, actually, I think your voice was breaking for a couple of seconds. So, uh,
Is it
can you
any better
repeat?
now?
Yes, yes. Can you repeat the VAE section? I mean,
Yeah,
the
that
third
is
point here.
happening. That is happening for the past few minutes. Maybe you want to re-log in.
Yeah, I
Really?
mean, you can try.
Yeah,
Let
Yeah,
me
and
just
it,
do
it
one
is
for
thing.
breaking
the
up.
previous slide also. Yeah.
Let me just do one thing. I mean, it might be a reason for my, like this. Can you guys hear me?
Yes, yes.
It's
Yeah,
good now.
Is it any better now?
Yeah, it's good. Now it comes for
good,
some
good.
time, then it gets noisy, then
Yeah,
comes some
it's
time.
crisp.
So that's how it
Yeah,
has been. Now it is good. Let us see.
I guess it is breaking again.
Man, just hold on. I'll just log
Yeah.
in on my phone. I think that should be perfect. Just give me a moment. I'll just do it right away. Can you guys hear me now?
Yeah, yeah, it's clear.
Everything's okay, right?
Yes, yes.
Yeah, yeah. So sorry for that trouble. Anyway,
Yeah.
I think so. I was just introducing high level, or rather, I was introducing Merlin over here. I think when we just left off. So in the first step, we are actually training some base models, one for each specific. I mean, sorry, B base models for a specific task that we're trying to solve. And then in the second step, we are trying to learn a distribution of these weights. And this distribution for the weights, this is kind of learned by a relational autoencoding kind of a setting, where the input is nothing but the weights that you kind of learned in the first step, and then there is a task specific prior. So this is in contrast with the standard VAE setting, where we have kind of like an isotropic multivariate distribution, which from which we are sampling the z's, right? So in contrast to that, here we are trying to learn a task specific prior. I'll get to the specifics in the next slide, but what the key takeaway over here is we are trying to learn a task specific prior, which is central to how we're kind of estimating and consolidating our distribution in the next step. So once we consolidate this learn the distribution, then we can sample any number of models from this distribution, and then we can ensemble them and predict. So this would be a nice point to take any question. Yeah.
Yeah. So is there a relation between B and E? Like now you are learning B-based network for
Mhm.
the you have. while ensembling your sampling E networks, like is there any relation, something like E should be a minimum of this many models or should be a maximum of this many models, something like that?
Yeah,
Is there any?
we tried investigating that, but then like both of them are really decoupled, because I mean this B is kind of like what you're kind of using to train the VAE per se, and then this is being consolidated. So and then I mean in a sense, like there's just a handshake between the two parts of MERLIN. So one part is where you're kind of like learning the distribution, and the next part would be like the sampling from the learned distribution. And we found that like I mean both of them are a bit disjoint per se, and like there's no direct relationship between this B that you have initially and the number of models that you kind of ensemble.
Thank you, Joseph.
Yeah, sure. Any other questions?
Joseph, why not
Yeah.
use a mammal type thing to learn uh, a point where you can reach the weights easier?
Right. Even there, I mean, my key kind of motivation was to kind of like to drift away from the data space and then go into, like this weight space and try to consolidate over there. So, I mean, like that is where I kind of like fundamentally am different from any of the, fine tuning, or rather, adapting the weights for better, adapting weights based on an initialization, so on and such methods.
Okay, got it. Yeah.
Sure. Yeah. Any other questions? Great. Okay. So let's dig a little bit more deeper into each of the specifics. So what we're assuming over here is like we do have a distribution p theta star, which actually which is a real distribution from which the weights for solving each of the tasks actually comes from. So we are assuming this to be like conditioned on Z, which is indeed conditioned on a task specific prior. So essentially what we're trying to learn over here is, or rather, if we had this ideal parameter theta star, then our life would have been perfect. But then estimating this marginal likelihood P of say given T is kind of intractable, because like the true posterior is intractable. So the standard setting in is that we kind of work in this kind of setting would be, like we try to estimate the lower bound, the evidence lower bound for that, and try to minimize that. Sorry, maximize that. And so this is where this is how we do have the elbow formulation, and this will be the lower bound. Now for till here, this will be the standard kind of the VA kind of a setting. But what differs in our formulation would be the prior that I just talked about. So this is how we actually model the prior. We assume the prior to come from a standard, from a normal distribution that is parameterized by mu t and sigma t. And mu t is indeed received from a learned a single layer network, I would say, which is actually conditioned on task. So these set of weights wt are being learned. Same is the case with sigma. So this is a learned task specific prior. So after learning a specific task, we indeed store the weights and this W mu and W sigma, so that later and T over here is would be, like any kind of a vector representation of that specific task that we are trying to solve. Okay. So this learning this task specific prior is indeed very important to MERLIN, because that is at the crux of, like how we are kind of storing away some kind of information specific to each task, which we would be using sometime later when we try to, like formulate it into some, or rather like whenever we want to recall something, we would be using the task specific prior, and then like from the prior we'll just sample as Z's and then use the Z to kind of sample back models from the consolidated decoder. So
Excuse me, Joseph.
sure, yeah, Puneet, go ahead.
Yeah, so are you learning these priors beforehand? I mean, or
No,
are you like learning them jointly with the
yeah,
jointly?
we are learning that jointly with the entire model. So after learning a task one T1, we, I mean, like, we'll be learning the entire model end to end. And after learning task one, we'll be just storing away those, W and W mu and W sigma.
But I mean, did you notice any kind of I mean, stabling, unstabling kind of things? Because I mean, you are kind of moving a latent space to a particular prior, and that kind of prior
Hmm.
is also kind of moving and updating. So
Right,
I mean, it's
right. Right, right. So I mean, yeah, to get this actually working was a bit difficult. So me to had to try around different ways to kind of,
Mhm.
make it actually working. To be honest, so over there, one thing that I found really interesting was that like I was just, I was just removing the non-linearity after right to learn. After this W. So this is just a linear
Okay.
network or a linear transformation of T, and that actually really works well.
I see. Oh,
Yeah.
okay. Mhm.
Joseph?
Hi, Srinivas.
Hi, Joseph. Actually, I have a doubt regarding equation 1 and equation 2. I mean, in
Uh-huh.
equation 1, the KL divergence is between the variational posterior and true posterior, right? Which
Exactly.
we don't
Yeah,
know.
exactly.
And you said we replaced it with the prior. I mean, after
Uh,
manipulating the equation
uh-huh.
in equation 2,
Hmm.
right? But I mean,
Yeah,
in general, this is the process, right? In general, people go with equation 2. But you said
right,
we have modified this thing, but it is
right.
actually okay. Go on.
Sure. Yeah, sure, sure. Yeah, good. Please complete. I'll take up from there.
Okay. I mean, you said this is the difference between what people have did before and if I remember.
Right, right, right,
But
right.
generally,
Yeah,
people.
yeah. I'll explain. I'll explain why.
Okay,
I'll
sure.
just share my entire screen so that it will be easier for me to
Okay.
switch between slides. So, that's a good question. Can you guys see my screen again?
Yes, 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 Joseph.
Yeah, yeah, great. So this is, this is a VAE paper, right? So in the standard VAE setting, what we essentially have here is like we have this prior over the latent variable z, and this indeed is taken as a standard normal. So does this clarify your question? For example, in the standard VAE setting, there is indeed this prior. This p theta z is indeed the prior over the latent variables in the variation lower bound setting, right? And this prior in a VAE is kind of taken as a standard normal and a centered isotropic multivariate Gaussian. And this is from here that we are kind of extending. We are taking it a level further and making this a task specific prior. Does that clarify? I think you're on mute. I'm not able to hear anyone.
Joseph.
Yeah, yeah, I can hear you now.
Okay.
So did
I
that
have
clarify?
small doubt, but I will ask you later.
Okay.
And one
Yeah.
more thing is that for training the variational autoencoder,
Uh-huh.
okay, we can assume that the total number of training samples for the variational autoencoder equal to the number of tasks.
It's not indeed the number of tasks. So it would be the number of, the models that we
Wait,
have here for training, right? The B. B.
B.
Yeah,
Here, train B model. Okay. In your experiments, what is the B value actually?
perfect. So that actually brings up to another very interesting question as to, like B is a huge vector, right? So B is actually the
Yes,
weight
yes.
weight vector of the entire neural network that you have. That
Entire
will be
neural
in the
network.
order of, right. And then you'll be having an encoder and a decoder to kind of like,
Hmm.
so here, assume you'll have around the 50 neurons over here, then will be 30,000 cross 50. That would be a huge network, right?
Huge network. Yes, yes.
Right. So that is too much to do. So that is not what you're actually doing. So what we're actually doing is like we are actually chunking the weights from that we're actually learning into over here. So each of the
Mhm.
psi are basically chunked into fixed size vectors, and those vectors are and those chunks are also conditioned based on chunk ID.
Mhm.
and those are what are really being encoded inside the the VA. And now that naturally kind of answers another part of your question, where like you have two small data points to train. So how are you training it?
Yes. Yes.
Yeah, sure.
Okay.
Yeah, yeah. So thank you for those really good questions.
Thank you, Joseph.
Yeah. Any further questions?
Yeah, so for each chunk, you have a separate VA architecture, right?
No, no. So the chunk size is kind of fixed. So so like take Psi over here, chunk it.
Mm-hmm.
So chunk size like can be, let's say, 100, and then like we will get 100 chunks from here, and each of
Yeah.
them are encoded, we think, using the same VAE. Okay.
Okay, but while sampling,
Hmm.
uh, how will you
Right.
differentiate, to which
Right.
chunk it belongs?
All right. That is why chunk is also conditioned.
Okay, okay, I got it. So you
Yeah.
say that it is chunk one, chunk two,
Exactly.
something like that.
Exactly.
Okay,
Exactly. Exactly.
okay.
And
Got it,
then
got it.
it's padded at the end. So that's how it's actually
I
done.
see. Got it. Mhm.
Sure. Yeah. 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 I'll just go ahead and share it like this so that it would be easier. Present now your window. Right. So yes, I believe my screen is visible again.
Yeah,
Perfect. Sure. So this is how we kind of learning this meta distribution. And suppose that we have learned, what we're essentially having is like we have this learn task specific prior. And this is what is kind of used for consolidation. So PI would refer to the mean and the sigma that we have seen for a like a scene task, or so after learning a new task, we are kind of consolidating the entire encoder and the decoder. And the way that we're kind of doing it over here is, like from the saved mu and sigma, or rather the w mu and w sigma that we saw before, we are sampling z from there in line number 3. And then from there we would be sampling the models corresponding to the task specific prior, and then all of these models would be used to update the mu and the sigma. So what is not being updated over here are the w's, which were the weights inside the task specific prior. So after learning each new task, this is how we would be consolidating the meta distribution that we are actually learning. Okay. Now, going further, now the next the only thing that remains is like, how do you kind of do the inference? The way that we kind of do inference can be either task agnostic or task aware. So for task agnostic, the only thing that we need to do is like we need to kind of like come up with a function that kind of aggregates the different mu's and sigmas that we actually have. So what we have found is a simple, averaging of the mu and sigma, and that essentially really helps working. So we're just taking the average of the mean and the sigma, and then sampling z from there. And then once you sample z, what we're essentially doing is like then we sample this model E. I mean, we actually sample E models from like E for ensampling. So we actually sample E models for like the distribution is conditioned on the Z, and then we fine tune each of the models on a very small set of exemplars that we have, that we keep aside per task, and then we ensemble all these models. So this is task agnostic inference. And the task specific inference would be something like, it's very natural, straightforward. We pick, we know which tasks are that inference, right? So we pick and choose the specific task specific prior, and then sample model from sample z from there, and then and do the same thing. Sample models from the learned distribution, fine tune it, and then ensemble them. So this is the inference pipeline. So that basically summarizes everything. So this is all. So going back, we just sample some data. So sample some data points, train a set of base networks, and then use those base networks to learn the parameter distribution, which is a task specific prior. And by after learning a new task, like we consolidate all the earlier tasks, with this learned on this parameter space, I would say. And then once we have this like consolidated distribution, we sample models from there, we fine tune it, ensemble them, and then get the result. So this is all it is. And what we have here is like we have comparison on 5 different data sets on 5 different baselines. So GSS was published in last year at NeurIPS, and then the other are also standard respectable benchmarks in continual learning literature. So two of the metrics that we actually have is accuracy. So accuracy is like after learning all the tasks, how accurately are you predicting all the tasks that you have seen till then? So that is the accuracy, and the forgetting measure is, after learning a new task, and if we are trying to test it on that new task, then obviously the accuracy will be much higher than that. Much higher at that point of time. So we'll say that accuracy, and then see how much is it decreasing after learning any of the other tasks. So then the difference between them is the forgetting measure, or the F that you see over here. So ideally it should be 0, and the accuracy ideally should be 100. So yeah, so these are the results that we have on a variety of data sets. For example, simple data sets like spread MNest. So permitted MNest is actually a domain incremental kind of a setting. All the other are class incremental. And we do have some results on mini mentioned also. So yeah, so this is the results. Now, something to note over here is like we have a series of things happening inside this method. For example, how many models do you want to ensemble? No, like is this model actually training anything, or like is any kind of consolidating happening? Is the VA learning any kind of meta distribution? Now, what is the proof or evidence for that? So there are a lot of things that are changing over here. Now let's step through each of them and spend some time. So first question would be, what is consolidation? How is it consolidating? Where is it consolidating? How do you say that it is consolidating in the meta space? Now, one way to answer all these is like, okay, if it's not consolidating, then the only reason why it should work would be, like you are sampling from an unconsolidated or rather a random VAE, right? We have some random stuff that is coming up from a VAE, and then you do have a fine tuning step. So that is doing everything. So fine tuning is the most important thing. So that can be one argument. For that, what we try to do is like, we just kept the VAE untrained. And then we're just sampling models from the VAE. This and then we're not doing the consolidation piece over there in the VAE at all. Now what we see is like there is a significant drop in performance when we do that. So we are indeed learning something good representations inside the VAE. Now, what if we do have the task information at Inference? So I told that like we operate in the both task aware and task agnostic setting. So all the results that we see over here, MERLIN is actually working in a task agnostic setting, while the baselines are working in a task, specific setting or task aware setting. Even then, MERLIN is better. So and over here, what we're doing is like, when we are having this extra task information for small data sets, there is a significant improvement of let's say 7%, but for larger data sets, there's not much of a significant improvement. So essentially, model is able to kind of incorporate this task specificity, or rather that extra information inside the network itself. Now, how much models do you want to ensemble? So we did an inflation where like we are just we're changing the number of models from 1, 30, 50, 100. So important thing to note over here, when we are jumping from 1 to 30, there's a huge jump. Like over here, there's a 4% improvement, there's a 9% improvement in mini ImageNet and so on and so forth. But then if you are increasing in much higher, 50 to 100, the improvement is not that much. So ensembling helps, it's really important, but at the same time, it's not very, very important. Or rather, like ensembling it, to very large number of models is not important. It's crucial because, small number of ensembling is actually required. And now I told about this chunk, right? Oh, sorry. And now this is about how many examples that we actually store in this exemplar set. Now we are changing it from 100 or 500, 1000 and 2000. And what we see over here is like when you compare to the other methods which actually make use of ensembles, Merlin is able to kind of make the best use out of the data points that we actually have. And for all the experiments that we had, we just had around 100 data points in the store. So how big is our meta model? So our meta model, by meta model, I mean the VAE. So the number of parameters that are in the classification model, which would be a standard. I mean, so if I compare it with the other incremental learning model methods, for example, regularization based or exemplar memory based and so on and so forth, all of them will have a standard classifier, fixed classifier on which they will be learning. And over here, we are not storing such a classifier per se, but then we are storing the meta model. Now we find that like the size of the meta model is indeed very small. One thing to note over here is like the size of the independent models that we are kind of training for the training in the first step, right? Even that, or even those are also very small models, and they are not big ResNets. So there is a significant drop in the like the VAE that we are actually using, the size of the VAE that we are actually using. Now we did talk about this chunking. Now, how important is that? And like what so and what will happen if we vary that? Now, if we so as we increase the chunk size, the thing is, the size of the VAE also increases that much. This will be the input dimension of the VAE and the output dimension of the VAE. What we see over here is like increasing the chunk size actually deteriorates the performance or in different data sets. At the same time, a chunking with around 100, it will kind of like link up to the number of data points to, let's say, 31,000. I mean, for us, that was kind of optimal. So we just went ahead with that. Now, this is a latent space of on the left. What you have is like I'm just sampling some data points from the learned task specific prior, and that is what and just plotting it. So this is what we have here on left, and on the right we do have a TSNE plot of the parameters that are sampled from the task specific prior. So this is what we actually have been ensemble and predict. So what we have over here is like there is clear separation in the task specific prior, at the same time the models that are sampled from there. Yes, and this pretty much brings me to the close of the talk. So this is what we do in Merlin, and we are able to kind of address this problem of continual learning to some extent. I'll be happy to take questions.
Thank you, Joseph. I think, it was a great talk, and apart from technical novelty, it also has a lot of engineering novelty
Yes.
also. The way you split chunks and all.
Yeah.
Yeah, it was indeed a nice presentation. So, if anyone has any questions, please, you can also unmute or you can also write them in chat box.
Hey, Joseph. Once again,
Hi,
congratulations.
bud.
Very good work.
Thank
Very
you.
good work. Always pleasure to learn from you with the clarity of thought and expression you do. Thank you.
Thank you so much, bud.
And how many tasks do you have total?
Right. So it actually depends upon the data set that we are actually using. So in split MNIST, what we have is like we have 5 tasks. Each task is trying to learn two characters in MNIST. So in permuted MNIST, what we have is like we just permute the data points so if we permute, the spatially so let's take MNIST. We do have an MNIST, let's say an image of one, right? In permuted MNIST, we permute spatially each of the points inside that specific image, right? So, and it's up to us as to how many permutations that we need to have. Now, for there, we did have 20 tasks, and CIFAR 10, it was the same case as split MNIST, where we are grouping classes by 2, so it's 5 tasks. So, CIFAR 100, it was 10 tasks. It was 10 into 2, 10, sorry, 10 into 10. Split image mini instant, it was also 10 into 10.
Oh, okay. Okay. So how does F change as you keep on adding more and more tasks one after the another? Is F really worsening from task
Oh,
1 to
right.
task N?
Right. Yeah, that's actually true. So we see a trend, like so after learning the last task, whether we are able to perform well on the earlier task, it's not ideal situation where you have a line that is parallel to the x-axis. No, it doesn't happen. It drops, but then it's significantly better than the baseline.
So this average accuracy score is score after you have seen all the tasks, right?
Right. I'll give a concrete example. For example, in
Mhm.
split MNIST, you are learning T1, T2, T3, T4, and T5. After T5, we do have the test set of T1, T2, T3, T4, and T5. Now, all the data points in the test set is evaluated on the model after learning T5, and the accuracy is kind of reported.
I see. And how this forgetting measure is defined? I mean, I don't know if I missed it.
Sure.
Uh,
I'll just give the concrete definition of that maybe. And for that, I might have to go back, stop presenting, again present the entire screen. The only reason why I was doing like window only share is because I can see the Google Meet on my side without disturbing you guys. Yeah. So
yeah,
the
not problem.
question, yeah, Puneet. So your question was how do you actually measure the forgetting, right? Yeah,
Yeah.
just
Mhm.
take the paper. Where is it? No, I don't think I have it here. Give me a minute. Right. So, right. So this is how we kind of define the forgetting measure. Now, after learning a new task, let's take T1. Now, after learning T1, we will be evaluating that on just the T1's test set, right? And we'll
Mhm.
have an accuracy over there. Now, that accuracy ideally should be the best accuracy for solving task one because incrementally, when you're adding, the accuracy actually drops down.
Yeah.
You would agree with that,
Mhm.
right? Now,
Yes, yes.
so that is essentially what we are doing. We are kind of measuring how far it dips. So ALJ would be, like the best accuracy that it has seen till then, and AKJ would be like whatever is the accuracy after learning any of the tasks. And now we are taking the max over all the 1 to k minus 1 tasks that you've already seen. And then we are
Mhm. I
measuring
see.
how much is that
Mhm.
drop. So ideally it should be zero, but then it doesn't go to zero. For example, in the single, what you have is like you have a single model, and that is incrementally learned without any incremental learning source added to it. So this has been
Yeah,
used for getting of 100 from or the 98. It's not able to kind of recollect anything that it has actually learned before.
I see. Mhm.
Yeah. So so this specific measure as like that was introduced in the AGEM paper or a GEM paper or AGEM paper, FAIR paper.
I see. Mhm.
Yes.
Uh, Also, Joseph,
Yeah.
for the
Good.
meta model, you have picked VAE.
Yeah.
Did you try any alternate models? Why did you narrow down to VAE?
Yeah, so the choice of VAE was because I wanted to manipulate the latent space. So the obvious question would be like, okay, GAN also has a latent space. Why don't you play around with that? So choice of VAE was because I was even mathematically it was much more like convincing for me to go with a VAE kind of a setting, where I would be kind of reconstructing the set of weights, and then we are learning that like the space of the weights, and so that was one reason why we went for the VAE per se. And like initially when we started off, and then like I think I can say all these things with this group. Initially when we started off, I was kind of like flattening up the entire weight vector, and then trying to encode it with the VAE without actually doing the chunking. Now, apparently that works, even that works, but the numbers are, numbers are also respectable, I would say. But like the size of the meta model is too much. It's so huge, and and that will not sell out. That is when we kind of came up with like, okay, can we try chunking and see whether it works? And yeah, chunking used to work. So all these things kind of added up one on top of the other, and then yeah, finally that is how we kind of went ahead with the current shape of Merlin. I would call it that way.
So can you elaborate? When you say chunking, what exactly you're doing to those weights?
Sure. Now let's again be concrete. Now we do have a model over here, right? A base model. Now that base model, assume it to have three fully connected layers. Okay. It's taking as input the standard image. So it goes from 28 cross 3 into, let's say, 500 cross 500 cross 10. That's indeed going to be a lot of weights, right? If I flatten up all those things into a
Right.
single vector. Now, what I do is I flatten it up, and then I cut it up into fixed size chunk, and I vary the number of chunk over here in this table, and at 100 chunks, 100, chunks with 100 items each, chunks with 300 items each, chunks with 1,000 items each, chunks with 2,000 items each. And then each of these 2,000 chunks are being encoded inside the VAE. And so something that is swept under the carpet over here is this is not indeed directly only conditioned on C, but then there is another extra piece over here which is a chunk ID, which is also going inside. That's used while inference for sampling.
Yeah, but when you sample a model or when you do ensembling, but you need all those weights, right? I mean, when you say chunk,
Right. So this is how we do it. We sample Z from the task specific prior. Then we fix Z. And then we change the chunk ID over here. We generate all those set of weights for the chunk. So if we kind of, I mean, this model is kind of learned conditioned on the chunk ID, right? So as we are modifying the chunk ID, all we are kind of doing is we are generating the weights of that specific chunk, and then we put together all these things, and then all these weights into a single model, and then reinitialize a specific model on this sampled weight, and then go ahead, do it again for the next sample for Z, and so on and so forth.
Okay, so your learning is based on the chunks, not all
Exactly.
all of them together, but kind of
Chunk ID, yeah.
leaving the rest of them fixed. The chunk is dynamic one. Okay.
So, I mean, Z is a big boy, and then chunk ID is also learned, or not learned. It's also conditioned on the chunk ID.
Okay, good,
Sure.
very nice.
Yeah.
Hello.
Yeah.
Hello.
Yeah. Go ahead.
Can you?
Yeah, I can hear you.
So, I have one doubt. I have one doubt.
Yeah. Go ahead, Sridhar.
Okay. So, I think, to my understanding, class incremental continual learning means if we learn 50 classes, then we are in the next task. We can teach additional classes, and this should work fine. So that's my understanding.
Exactly.
So, maybe I will explain the situation. I just want to make sure if means just to check if this is applicable in that situation or it can improve that situation.
Right. So, yeah, go ahead. Please finish. Yeah.
We have a kind of face recognition model in an office setting or something.
Sure.
So we trained the model to identify all the employees. Maybe 50 employees are there. We trained the model to classify or recognize all the 50 employees.
Sure.
So that was the task one. Task one was to train the 50 employees.
Sure.
Then after some time, new employees joined in that office.
Sure.
Maybe three new employees came, and now we have to extend this model. So I just want to know. I just want to get the definition of task 2 with MERLIN in place. Means I just want to confirm if task 2 will be training only 3 classes
Hmm.
the three new phases, or
Hmm.
training all 53 phases.
Right, right.
If
So yeah,
it is there.
yeah. So thanks for the question. So, yeah, I mean, in a class incremental setting, if you want to pose your problem, task two will contain three classes, or rather three, I mean, identities, I would say.
Okay.
Yeah. And the task
So,
one would be the 50 identities. Yeah,
okay. So, task one, 50 employees. Task two will be only training these three new employees, right?
exactly.
Okay. So, if again new employees join, then we will define task three as training two or three employees more.
Exactly. Exactly.
Okay.
That's
So,
exactly what we have here in this figure.
okay.
Initially, this is
So
what
then,
you had for, like your 50 employee. Then three more employees joined. Then 10 more employees joined. This is it. This can go till infinity. And the model
okay.
per se, it should be capable of recognizing all the employees that are seen till that point of time without explicitly retraining from scratch each time on all the
Yeah.
tasks or all the 50 or like, I mean, 60 employees that you have.
Okay. Then, during the inference time, should we
Hmm.
actually evaluate all the models, like
Yeah,
the model which was
um,
trained for 50, and then the
right,
model which was trained for 3?
right, right. So there is a very important difference over there. You don't have different models. You just have a single model. You just have a
Yeah.
single
Oh,
model which should be capable of doing everything.
yeah. Means, mm,
Meaning, so suppose you have a function f
yeah,
that
go
tries
on.
to learn your 50 guys. That the same function f would be learning the extra three guys, three identities without actually forgetting the initial 50 identities. It's the same model.
Means one thing is like for the task three, the test set will be having all the 100 employees or something,
Perfect. Right.
right?
You're correct.
And it will be able to identify, right?
Exactly. Exactly. Yeah. That's the definition of
Okay.
continual learning. Yeah. That's true. You're
Okay.
absolutely correct.
Okay. Thanks. Yeah.
Yeah.
Yeah, hi Joseph. So
Yeah.
I have one more question.
Sure.
I think, I mean, I don't know how to put it. So, like you here tried to kind of work on weight spaces. I mean, try to generate weights of the network. But I mean, one can also do, they can also kind of generate the change in the weights, right?
Mm-hmm.
What I say is that you have some initial model which is trained on
Mm-hmm.
some task one, and you want to kind of adapt it to task two. So maybe like condition on the task, you can generate how much weight should be shifted.
Mm-hmm. Mm-hmm.
Uh, so I mean, is it something, I mean, you tried, or I mean, do you have any thoughts on this?
Mm. Yeah, Puneet, so would that be linked a little bit into our weight imprinting kind of a setting?
Yes, yes, something
Yeah,
like that. Yeah.
right. So, I mean, I haven't personally tried that, but then
Mhm.
the other part of the same question would be, I mean, yeah, suppose we are trying to learn. So, I mean, let me try to understand. So, are you saying that we will learn how to modify the weights, or
Yes, yes. Yeah. Uh,
that's also would be something like, we are meta learning how to modify the weights so that like the life will be beautiful after learning all the tasks,
yes,
right?
yes,
Yeah, so
yes.
there are a suite of like, I mean, a mammal has been attacking continual learning for a while.
Mhm.
So
Yeah.
there are a lot of works in that space. So even in this NeurIPS, there are a lot of, mammal continual learning kind of methods like BA mammal. I don't remember what exactly they are, but yeah,
But like in mammal, you don't kind of generate updates, right? I
right.
mean,
Yeah,
I'm necessarily
yeah,
talking about your exact same framework. I
right.
mean, what if instead of, I mean, generating weights, you kind of
Right.
in,
Yeah, so
yeah.
exactly. Yeah, I get it. So that is basically weight imprinting plus, continual learning, right?
Yeah,
And
yeah.
specifically, I've seen one paper, and I know like weight imprinting. I mean, weight imprinting is very exhaustive, and like our a few short methods. But there is one paper that I've seen, and like weight imprinting being used in. Oh, no, that was also not in continual learning. That was on few shot object detection. But then I would say that it would be a very low hanging fruit. I'll be surprised if no one else would have tried that. But then
Hmm.
no paper really comes back to my mind right now.
I see. Okay.
Yeah. Yeah,
Mhm.
but then I mean, learning, let's say a function g of x that takes your f of x and spits out, not spits out, like generates out, like a weight for a continual a model. I think that would be a very interesting thing to look forward. Yeah.
Yes, I mean, I have seen some works which kind of uh, uses LSTMs and RNNs to kind of generate weight updates because, I mean, if you
Yeah.
see the weight update procedure, it is similar, like, I mean,
Right.
it's temporal kind of thing.
True. True. I agree. I agree.
Hmm.
Yeah. Like,
I
yeah.
see.
I personally haven't tried that, but then yeah, I agree that it's a good direction to kind of like
Hmm.
look forward. Yeah.
And
Yeah. But
Okay,
Joseph,
thanks.
yeah.
one thing, have you looked at federated learning in this context of Merlin?
No. So by federated learning, I think you might be referring to, like, can I split it up into pieces wherein I have I mean, on node service and then a federated service and then like data going forth here and there, and then maybe learning a little bit on the node and then learning the rest on the server and so on and so forth. Is that what you're referring to?
Right, right. Yeah. So don't move the
Hmm.
data to the server, stay at the client or wherever, and then learn at the edge, right?
Yeah, I would say that I mean the framework of Merlin would be, I mean, would be ideal to do something like that because we are just I mean learning everything. I mean like learning the new task at the node at the endpoint, and then I mean sharing over the weights maybe to the or I mean maybe even you can consolidate in the client or maybe share the weight W's back to the server. Maybe we can think about something like that, but then like I mean personally I haven't I haven't put that shoes on here.
Okay, sure. No problem.